Good morning, everybody, and welcome. It is indeed a real pleasure to be here today. I've not been to, now see if I can say it right, it's Thessaloniki, is that right? Okay, good. So I've not been here before. I've been to Greece a couple of times, but I've not been here before, so it's a real pleasure to be here and see so many people at this presentation. So in terms of the keynote, what I really want to do is talk about JDK 9 and to discuss what is going to change. Because if you look back at JDK 8 was all about changing the language, the introduction of Lambda expressions. It was about adding more functional style of programming to Java with the Streams API. And so it was a big change for Java. JDK 9 is also going to be a big change, but in a very different way. What's changing in JDK 9 is all about modularization. Now, there are other things as well, but the primary thing that's happening in JDK 9 is modularization. So that's what we're going to go through in this presentation and find out what it means to you as developers. So the first thing we need to talk about before we get into the actual module part of this is about some of the structural changes that are taking place in terms of APIs. And this is kind of interesting because if you go right back to the very beginning of Java, so let's have a show of hands. Who here has used JDK 1.0? Okay, a few people, not many, but a few. So I remember, because I'm old, that JDK 1.0, there were about 200 classes in the class libraries. I remember thinking that that was really good because 200 classes and methods, I could actually hold all of those in my head. So I didn't need to refer to the documentation all the time. Type has got on, and what you find is that in JDK 8, there's somewhere around 4,500 classes in the standard class library packages. I certainly can't hold all of those in my head anymore, which is a good thing as well, because now I don't have to write a list class, I don't have to write a SQL connector class, I don't have to write all sorts of different classes, because they're already there. But the evolution of that has caused some problems. It's been a gradual thing through many releases, but we've kept adding APIs to the same big jar file. So we have rt.jar. Now, if you look at rt.jar, what you find is all of these 4,500 classes that you are allowed to use. But there's also a whole bunch of other classes in there which are necessary to make those 4,500 classes work. But you're not really supposed to use them. So if you look at the sort of classification of those, there are supported public APIs. Now, these fall into a range of different packages. There's java.star, there's javax.star. And these are ones which are the Java SE defined APIs. And these are the ones which are part of the specification. You're perfectly allowed to use them. They're all documented, all ready to use. But there's also some other public APIs included in there. And these are ones which are specific to, like, the JDK. So they're not part of the Java specification, but they are public APIs. There's things like com.sun.star, and there's things like a web server is included in there. There's some JDK.star APIs, and these are ones which are, if you want to use the compiler programmatically rather than from the command line, you can do things like that. But then there's this whole group of classes which you're not really supposed to use, and these fall primarily into the sun.star package. The most famous or infamous of these is sun.misc.unsafe. Now, I really like sun.misc.unsafe because there's a clue in the name. Unsafe. You're not supposed to use it. But lots of people have. So this causes some issues, some problems, as we'll see. Now, in terms of compatibility, one of the great things about Java is that right from the very beginning, Sun and then Oracle have always been very focused on backwards compatibility. So the general rule is that if you only use supported APIs in your application on version N, then it should work on version N+1 without any changes. There's been a couple of points where that might not necessarily work, but on the whole, very good in terms of backwards compatibility. There's nothing worse than taking code which works and having to modify it for a new version of a platform in order to make it work, because you're just wasting time. Now, a long time ago, in terms of the Java standardization, it was said that Sun and then Oracle could remove APIs from the standard packages. So it was documented, and that was made clear that that was what was going to happen, but only with advance notice. So you would be told well in advance when these things were being removed. And if you look at JDK 8, there are a number of deprecated elements in the APIs. In fact, there are 18 interfaces, 23 classes, 64 fields, 358 methods, and 20 constructors. I know this because I wrote a blog entry on this recently about deprecation, and I wrote an application that counted them all up. Of those, how many do you think have actually been removed? Anybody? None. None have ever been removed until now. So, JDK 9 will introduce some incompatible changes. There will be some things that you will need to be aware of as developers, that when you move your code from JDK 8 to JDK 9, there may be some things which will affect your application. I'm guessing that most of these won't be a big issue, but it's good to be aware of them just in case. Now, first of all, there's some encapsulation of JDK internal APIs. I'm going to talk about that in a bit more detail in a moment. There are also going to be a small number of APIs that will finally be removed. So deprecated APIs that will actually be removed from the standard libraries. 6 methods are going. They're all add and remove property change listener, and they fall into 2 classes, which is Pack 200 and Log Manager. So you might be thinking to yourself, well, what have those 6 APIs done that's so bad that they have to be removed? And I'll come back and explain that a little bit later. They have already been flagged. They've already been deprecated in Java SE 8. So the requirements have been fulfilled in terms of advance notice. There is a binary structure change in terms of the JRE, the JDK. So if you rely on particular files being in particular places, you may need to change your application. There's a new version string. So again, if you rely on the version string being a particular format, you may need to change your application. And one other small change is that a single underscore will no longer be allowed as an identifier. So hands up, anybody who's used a single underscore as a variable name. Okay, a couple of people at the front there, that's fine. Now, originally I thought, well, that's really, that doesn't make any sense. That's a very bad idea. But then somebody pointed out to me that actually there's a very good situation where you could use a single underscore as a variable name. And that's if you have a lambda expression that has a single variable, and I'm hoping this is where you've used it. Yes, good. It's a single variable in a lambda expression that you don't use in the body of the lambda expression. And then it does make sense. Unfortunately, the decision has made that in JDK 9, you won't be able to do that anymore. A couple of other things that have been removed in JDK 9. These are things which are primarily used by application server vendors. So the endorsed standards API override mechanism and the extension mechanism, which are both used when you're loading additional classes ahead of time before the application starts. Now, both of those have gone away because of the way the module system works. So, again, it probably won't trouble many people. So let's have a quick sort of discussion here. Right, the most popular unsupported APIs that are used by people. And Oracle did some analysis. They took all of their code and they looked at the Java code and middleware code and so on. And they analyzed how many times they had used the unsupported APIs. So does anybody want to have a guess, shout out, what the #1 most popular unsupported API that they used was? Anybody? Okay, I'm not hearing anything, but anyway. So the most popular one was Base64 Encoder. That was the one they'd used most times. #2 was Sunmisk Unsafe. So anybody want to guess what #3 was? I'm only going to go through 3. Decoder, very good, yes, thank you. So I thought that was kind of interesting because obviously they're doing more encoding than decoding. But anyway, so that was an analysis that they did just to find out where they used the unsupported APIs. So they had an idea of how to approach this. And what has been done is that the internal APIs have been classified into two groups. There's what are called non-critical APIs. And these are ones which either have virtually no use outside of the JDK, so nobody is actually using them, or they're used only for convenience because now an alternative exists. Base64 encoder and decoder is a good example of that because now there is a public API. Prior to JDK 8, there wasn't, so people use the internal one. But then there's these critical ones, and these are ones where the functionality that is provided by them, and MISC Unsafe is the best example of that, is very, very difficult, if not completely impossible, to replicate outside of the JDK, because you actually need access to the underlying JVM things, which you can't do just using standard Java APIs. Now, the idea originally for this was that all JDK internal APIs would be encapsulated in JDK 9. And that would mean that anybody who'd used any of the non-public APIs would have to figure out how to modify their code to get around this problem. But a lot of people were very upset about that, and they said, well, we know we weren't supposed to use MISC Unsafe, but we did. So what are we supposed to do in JDK 9? And the decision was made that that was going to be a bit harsh, so there needed to be a better migration path away from this. And that's where what's called JEP 260, the JDK Enhancement Proposal 260, comes in. And what this says is that all the non-critical JDK internal APIs will be encapsulated. These are the ones we don't really kind of care about. All the critical APIs for which an alternative exists will also be encapsulated. So again, there may be changes required to code if you've used one of these critical internal APIs, but there is an alternative you can use instead. Any which can't be replaced easily are not going to be encapsulated. So some MISC Unsafe will still be available in JDK 9. They will be deprecated, and in JDK 10 or maybe later, then they will finally be removed. But in order to avoid problems with people's applications, a new public API that provides similar functionality will be provided. So this gives a good migration path so people aren't going to have application code that just suddenly stops working and they can't change it to make it work. If you want to use the internal APIs, then you will have to add a command line flag when you start the JVM to say, yes, I really do want these available. To help you, there's also a tool that's been provided since JDK 8, which is called JDEPs. And what JDEPs will do is analyze a jar file, and it will look at all the APIs that are being used by that and give you a report so you can see if you're using internal APIs, if you're using APIs that you need to change. I suggest that in addition to running this on your own code, it's a very good idea to run it on all of the jar files that you're using from third parties, so you can be aware that even if you haven't used any of these APIs, some people that you're using code from may have done. So you might need to ensure that the flag is turned on in order to get your application working. So that's the details about the structural changes in terms of the APIs. Let's start looking at what Project Jigsaw is and how the module system works in JDK 9. So the first thing is, what were the goals for Project Jigsaw? Now, even Mark Reinhold will admit that Project Jigsaw has been going on for some time. It first started back in 2008, so it's been going on for 8 years now, and hopefully in July next year, it will actually finally be delivered in its complete form. You can kind of divide the goals into two areas. The first applies to the JDK itself, and the idea here is to make Java SE and the JDK more flexible and more scalable. Because there are 4,500 APIs in the class libraries, no application is ever going to use them all at the same time. So it's quite a burden to have all these APIs in the runtime for every single application. The idea then is to break it up into smaller chunks so that you can say, I need SQL, I need XML, I need logging, these types of things, and put only the modules you need for your application together. That way you can build a runtime specifically for your application. Things like the Internet of Things, embedded devices, need smaller footprint. Microservices, again, if you're using that and you want to encapsulate, in effect, a service within a runtime, then minimizing the footprint of the JVM and the JRE is also a good idea. It's also about improving security. So if you reduce the number of APIs that are available publicly in an application, you're reducing the attack surface that people have available to try and break into your application. It's about improving maintainability. It's about improving performance and the way that things like the class loader work, those types of things. The other side of the goals of Project Jigsaw around application code. And it's about how to simplify the construction and deployment of applications. So it makes it easier for you to build your applications. And as it says here, to eliminate Classpath hell. You know, we're aware of the issues that there are to do with the Classpath and how you have to configure it. And again, we'll talk more about that in a little bit later to see how we can get around that kind of problem. So the fundamentals of a module. A module is just a grouping of code. In Java, we already have this kind of idea. We have classes, and classes are grouped together in packages. So you put classes which have similar functionality and need to be grouped together into a package. A module is really just the next level up. So it's a way of grouping together packages which group together classes. But it kind of goes beyond that because a package obviously is just Java code. A module can include other things as well. A module can have native code in it if you want to do some JNI and you need to package native runtime libraries. It can have resources. If you need translations for messages in your application, you can put those as resource files. And if you need configuration data, property files, those types of things, all of that can go in a module. So I've just given an example here of a kind of module that I created, which is called com_azul_zoop. Within that, there are two packages, alpha and beta, and they have a number of classes within them. How do you declare a module? Well, in order for a module to be a module, it needs a module-info.java file. And in its simplest form, what you have in the module-info.java file is just a declaration of the name of that module. So you have module, then you have the name of the module, and a set of empty braces. A lot of people look at that and they go, ooh, hang on, does that mean that module is now going to be a reserved word? And the answer is yes and no. Yes, it is going to be a reserved word, but it's what's called a restricted reserved word, which means it's only a reserved word if you use it within the module definition. If you use it within your code in a Java application, then there's no problem. So you don't have to worry about not being able to use module as a variable name anymore. So you create a module-info.java file, and you put it at the top level of your package structure. And that's how you define the name of your module. In that form, it's not really a whole lot of use. So we then need to define other things associated with the module. Modules are most likely going to have dependencies. So one module will require packages and classes from another module. So we can state that explicitly, and we can say module com_azul_zoop requires com_azul_zeta. So there's a dependency between our Zoop module and our Zeta module. We can also then create an app and say that we have a dependency from our app module on the Zoop module, but it also requires SQL. And that's one of the standard JDK modules. We'll, again, come back to what modules there are available a little bit later. But you can see now that we have dependencies on both Zoop and on SQL. What that allows the compiler to do, and also the JVM at runtime, is to build a dependency graph. And so we end up with the idea that our app depends on Zoop, Zoop depends on Zeta, and we also have a dependency from app to SQL. All of the modules in our system have a dependency on java.base. Java.base has all of the fundamental classes in it that you need for any application. Things like string, integer, char, so on, those types of things. You don't explicitly have to state that in your module definition. So there's an implicit dependency on java.base for every module. And then what we might find is that things like java.sql also have dependencies on other modules within the JDK. So we say that SQL has a dependency on XML, also has a dependency on logging, and we build a full dependency graph in the compiler and also at runtime. So any requirements in terms of resolving particular classes, resolving particular methods, can be done using this graph. The next issue that we have to deal with is the idea of readability versus dependency. So we have part of the graph here where app depends on SQL and SQL depends on logging. And what we might end up with is a piece of code like this. So we create a reference to an SQL driver. And then from that driver, we get a reference to a logger. And we want to log a message. So that's a very simple piece of code and typical kind of thing that we might want to do. The problem that we have with this is that although app declares a dependency on SQL, there isn't an explicit dependency declared on logging. So when the compiler comes to resolve the use of the logger class, it will say, okay, well, we can see SQL, but we can't see logging. So how do we resolve the use of the logger class and the get parent logger method and so on? So what we need to do here is solve that problem. Now, we could do that by simply saying, well, okay, app has to declare a dependency on logging in order for it to work. But that's a bit kind of messy because it means you as a developer have to remember to add those dependencies. So to get around that, what we have is a modifier. So now in terms of SQL, SQL can say that it requires logging, but it does it in a public way. What that does is gives us implied readability of logging to any module which has a dependency on SQL. So now, any module that declares dependency on SQL will also have access to any of the public members of the logging module. We don't have to state it explicitly in our app module definition. So that solves that problem. What we then end up with is extending our dependency graph into an implied readability graph. And so we end up with a situation where both XML and logging have implied readability. So app, having a dependency on SQL, also has access to the XML and logging public members from those modules. Now, one of the things that you have to be aware of is that when you create this graph, in terms of defining your dependencies, it must be acyclic. So there must be no loops within your graph. If Zoop has a dependency on Zeta, Zeta can't have a dependency on Zoop, because that would give you a cyclic dependency. So you can't do that. Package visibility. Now, package visibility is where things get a bit more interesting, because if you don't define any exports, nothing in the module will be accessible outside of the module. So if you declare a dependency on it, there's nothing there that will actually be available to you. So you have to explicitly state which packages you want to make available to other modules that have a dependency on this one. So in our Zoop module, we can say that we require Zeta, and then we export alpha. So any module that has a dependency on Zoop will have access to the public members of the alpha package. We can also make that a restricted visibility. So we can say we export Zoop beta, but only to Com-Azul app. So if another module comes along and has a dependency on our Zoop, it won't be able to see the public members of beta unless it's called Com-Azul app. So you have a situation where, in terms of the theta package, that is not accessible externally. It can only be used internally within the Zoop module. Alpha can be used by anybody who has a dependency Beta can be only used by the Com-Azul app module. It gets even more complicated than that. This is a fairly recent introduction. So there's now the idea of what's called a weak module. So if you define a module as being weak with the modifier, you don't need to specify any exports. And in fact, you shouldn't specify any exports. A weak module will export everything. So it's kind of like saying export star. Things get even more complicated. One of the things that's happened more recently is the issue around reflection. Because there are certain situations where you have things like service loaders which require access to packages and classes which they do only through reflection. So there needs to be a way to allow certain modules to access elements of the API using reflection. So now what we can do is we can actually go even further and we can say, okay, our module Zoop exports alpha, exports beta to app, and also exports privately the theta package, which means that you can't see it if you're just compiling against it and use it generally, but you can if you want to use reflection. So if you use deep reflection to access the elements, you can do that. But otherwise, you can't see the elements of that package. So this then brings us to the idea of accessibility. And accessibility is really sort of a two-way thing. In order for one module to use packages and classes from another module, two things have to be satisfied. The first is that the first module has to specify a dependency on the second module. But the second module must also export the required packages. So as long as there is a dependency and an explicit export, then the public members of that package will be accessible to the first module. And this is one of the things which, to me, is kind of a fairly fundamental change in terms of Java at the language level, which might not be apparent at first. Because if you think about accessibility in terms of classes, methods, and fields, what we have is this well-known situation in Java. So you have public accessibility where anybody can access those elements. You have protected, which means only subclasses of that class can access those elements. Package private, so only elements, only classes in the same package can access those elements. And private, which means only within the class. Yes, we're all familiar with that. That changes a bit in JDK 9. Because now we have the situation where you can have public to everyone, you can have public but only to specific modules, and you can have public but only within a module. So the definition of public changes somewhat in JDK 9. It's not like it used to be where anything that was within your class loading was accessible to you. It's now public doesn't necessarily mean accessible. It's it means only if that particular element has been exported from the module will it be accessible to other modules that have a dependency on it. Now, this is a bit of an eye test chart, so I'm thinking that the people at the back probably won't be able to read this, but don't worry about that. This was the original way that JDK 8 was taken and separated up with the idea of making modules from it. So clearly the idea is that in order to simplify rt.jar and move away from 4,500 classes in one jar file, you want to break it up into logical units. And this was the sort of first idea that was created. Don't worry about the individual bits in there. What I want to highlight is a couple of things here which demonstrates the problems that the developers had in terms of creating this sort of graph. Because if we look at a bit more detail, this is a small part of that graph. And there's a package here, or module I should say, module here called JAX-WS, so web services. And that has a line, an edge in the graph that goes to the beans module. So there's a dependency between JAX-WS and beans. Okay, you think to yourself, okay, that kind of makes sense. Yeah, so web services uses something from beans, so there's a dependency there. Fine. Let's look at another part of this diagram, and what we'll find is that on the right-hand side is the beans module that we've seen before. And on the left-hand side is a desktop module. And there's an edge in the graph that goes from desktop to beans. So there's a dependency from desktop to beans. Okay, again, you think, yes, they've used beans, so there's a logical dependency there. But there's also another edge which goes back. So there's a dependency between beans and desktop. The problem here is it now means that there's a dependency between JAX-WS and beans, which has an implicit dependency on desktop, which means web services depends on desktop. And so if you're trying to separate out these modules, it's very difficult to say, well, okay, I only want web services, but you also have to include the desktop, the AWT stuff. And so you go and you dig into this in a bit more detail, and you go, well, why is there this dependency? What happened that meant that beans depends on desktop? And the answer is that way back when beans were being developed, there is a thing called a bean descriptor. The bean descriptor has things like fields which are a string to give the name of the bean. Also has a string which has the description of that bean. And I can only imagine that they actually gave this task to an intern. And the intern said, right, I'm going to make the bean descriptor really, really cool. I'm going to add more features to it. And so they thought, right, what else could we put on a bean descriptor? It's like, why don't we have an icon? Let's have a little graphical icon that you can use to represent this bean. And so in order to do that, you have to have some way of rendering it, which requires AWT. So beans has a dependency on AWT. Therefore, JAX-WS, because it has a dependency on beans, also has a dependency on desktop. So that was a very difficult thing that they had to do in terms of separating out all these dependencies. And that goes back to the 6 APIs that are finally being removed from JDK 9, is because of this trying to separate out all the different modules within the 4,500 classes in rt.jar. So this is now what the platform module system looks like in JDK 9. This is actually slide 1 of 2. So we have java.se. I won't go through all of this, but essentially you've got Java SE, which is called a meta module. So that includes a large number of other modules. So there's things like the compact profiles, which were introduced in JDK 8. So there's modules specifically for that. There's all sorts of things like management, RMI, scripting, desktop, and so on. And as I say, all of them depend implicitly on java.base. And then you've got another meta package, which is called java.se.ee. So yeah, I know, it's a bit confusing, but there are a lot of modules and packages within the Java SE runtime which relate to java.ee. So web services, naming, some of the Corba stuff, transactions, all in there. And so they've created another meta package which is called se.ee, which then includes all of these things. So it gives you a different way of configuring the modules that you need for your application. So let's briefly talk a little bit about how to use modules. So the first thing is, we want to move away from class path hell. So the easiest way to do that is to have a module path. So now we have a module path which looks very much like a class path. So you have a series of directories which have the modules in them, and so you specify the module path to resolve the modules that you need for your application. And then you can use that in terms of compiling your code in exactly the same way that you would use a class path today. So, okay, module path, modules, compile your code, you get class files. And when you want to execute the application, what you can do is you can say, okay, run with this module path, and then give the module name, and tell the system what the main class is within that. So I'm sure you're looking in that going, well, how is that an improvement on what we had before? Okay, bear with me. There is some improvement coming. But in this kind of basic form, it doesn't actually look any different, except it's called module path rather than class path. How do we create a module? Well, we create a module simply by generating a jar file. There's another format called JMods, which is used by the JDK at the moment, and it may be used in the future for application modules. But right now, you use a jar file. And in order to make a jar file into a module, all you have to do is include at the top level the module-info.class file that was compiled from your module-info.java file. So you create your jar file, and suddenly you have a module. You can then also use the -p option on the jar command, which is a new one, and that will give you some descriptive information about what your module is. So it'll take the information from the module-info.class, tell you the name of it, it'll tell you what modules it requires, and if you specify a main class, it'll also. And then things get a little bit simpler, because now we can simply say, run my module, and because the module includes the main defined in it, we don't have to specify that explicitly, and the JVM can then pick up the main, start the application, and run it. We then have the idea of linking. And linking is about building a runtime which is specific for your application. So you can have a JVM and a JRE installed on your machine, and you can run in exactly the same way as you do now. But if you're looking to minimize the footprint of your application, you can link it in order to only include the modules that you require for your application. Now, in its simplest form, what we've done here is just to create a very simple runtime which has one module in it. So it's got java.base. So actually it's not going to do anything useful at all. But what it does is it demonstrates that you can build a runtime that has all of the structure of the JRE, but only contains one module, java.base. And if you then run the Java command within that runtime, and you say list mods, it will show you one module, java.base. If we make that a little bit more realistic, a bit more useful, what we can do is we can say, okay, we have our application, com as all app, and we've defined all the module dependencies for that, so let's J-link it and create a runtime for that application. So we specify a module path, we add the modules for the app, and create an output into my image. And then, if we go into my image and we run the Java command there with list mods, what we're going to see is we're going to see java.base, java.logging, SQL, XML, app, Zoop, and Zeta. So all of the modules that we need are in there. The compiler and the runtime have analyzed the dependencies, created the dependency graph, figured out which modules are required, and only included those in the runtime. But all of the ones that are necessary are there. Now, the observant amongst you might be looking at this and going, ooh, I see a thing which is saying at 9.0. I see a thing which is at 1.0. Does this mean we have versioning in our application code now and our modules? And the answer is no. This is something where you would think that versioning would be a very useful thing to have. But the version numbering here is for information purposes only. It has no bearing on how things actually get resolved in terms of your application and the modules and the dependencies. And I actually included the quote here from the state of the module system, which is in effect the definition of Project Jigsaw at the moment. And it says, it is not a goal of the module system to solve the version selection problem. I think this is a bit of a missed opportunity. I think it would have been really nice if they had included versioning, but it seems it's really hard, so they've decided at this point they're not actually going to use versioning. Application migration. So this is quite important because clearly with a new module system, how do you take an existing application and migrate it to run on the JDK 9 with modules? So here we have a typical application in JDK 8. At the bottom, you have the monolithic JDK, one big rt.jar file. Then you have a group of third-party jar files that provide frameworks and all those sort of good things that you need in the middle. And then you've got the jar files at the top, which are the application code that you've written for your application. And the way that this works at the moment is that all the jar files that you have above the JDK are defined on the class path. So this is where our class path hell comes from, is that we have to define all of these jars and point the JVM to them and let it find them. So how do we now move to a situation where JDK 9 separates up the monolithic runtime into a set of modules? Well, what we do is we create a single module. We actually have a thing called the unnamed module. And essentially, the unnamed module is anything which turns up on the class path. So the unnamed module will work with the module system of JDK 9 so that it will, in effect, have a dependency on all the modules which are available in the JDK. That way, you can take an application that you've written for JDK 8 and earlier, you can use the class path, you can continue to do that, and simply run it with JDK 9. You need to make no changes at all from the point of view of running that application. You can simply say Java minus CP, blah, 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 application, and it will run unchanged. So you can effectively ignore the module system completely if you want to. So by using the unnamed module, everything just runs exactly as it would do before. That's the most important thing. Just take your application, run it on JDK 9, and it will run without any problem. But let's look at a more kind of realistic example here, where we've got a group of jar files, and we want to see how we can migrate that to using the module system. So I've got a group of jars in the middle there. I've got libgl, gluegen, and joggle for some sort of graphics application. And then I've created two jar files at the top. I've got my app and my lib. Great. Now, clearly, I could run that using the unnamed module, and everything would work exactly as I wanted it to. If I do that, I need to use classpath hell, where I say, minus classpath, my app, my lib, libgl, gluegen, joggle, and it all works. But, we want to do better than that. We want to use the module system. So what I could do is I could say, right, I'm going to take my app.jar, and I'm going to take my lib.jar. I'm going to create the necessary module-info.java file, compile it, put it into the jar file, and I'm going to turn it into a module. So now I've got modules for my application code, and I've got modules at the bottom in terms of the JDK and the runtime. But the problem I've got is, how do I specify dependencies in terms of my app? So it's easy enough to say, okay, my app depends on my lib, and I can say it depends on base, it depends on SQL. But how do I specify dependencies on these three jar files that I've got in the middle? Because I've got libgl, gluegen, and joggle. They're not modules. So in terms of my app, I've got a problem. The other problem is, you could say, well, okay, I'll leave them on the class path and make them part of the unnamed module. But the problem that you have there is you can't specify a dependency on the unnamed module. So how do we resolve the situation of these three in the middle? What we really need is a situation where everything is a module. So we want libgl, gluegen, and joggle to be modules as well. Okay, so I could take the hard approach, and I could say, right, I'll take libgl, I'll unpack the jar file, I'll figure out how to create a module-info.java file, I'll compile that, I'll repack the jar file, and then I'll end up with a module. But that's kind of hard work, especially if you've got lots of jar files in the middle there. You really don't want to have to do that. So the solution is to figure out, firstly, what are the dependencies. So we look at all the dependencies and we go, okay, so dependency between this module, that module, so on. Then there's this other thing called an automatic module. If you take a jar file which doesn't have a module-info.class file in it, so it's just a old-style jar file, and you put it onto the module path rather than the class path, it will become an automatic module. So you don't have to have a module-info.class file in there. If there is no module-info.class file, then the name of the module will be whatever the name of the jar file is. So you've got no way of defining it within the module itself, so it will automatically be the name of whatever the jar file is. It will export all of its packages, so you have no control over which get exported, which don't get exported. And more importantly, it will also have a requirement, by definition, on all other modules on the module path. So that solves the problem, because now we export everything, we have a dependency on everything else, so everything will resolve itself when the compiler and the virtual machine actually run your application code. So what we end up with is a dependency graph that looks a little bit more complicated, because now the three automatic modules that we have in the middle export everything, and they also have a dependency on all the other modules in the module path. So everything depends on everything else, in effect. And the observant amongst you will go, well, hang on, earlier on you told me that we can't have cyclic dependencies within our module graph. But if everything depends on everything else, in terms of automatic modules, there must be cyclic dependencies in that graph. And the answer is yes, there are. So I've told you you can't do it, and now I'm telling you can do it. The answer to that is, if you look at the way that it's been defined in terms of the module system says, for automatic modules, we the virtual machine or the compiler, will figure out how to eliminate the problems of the cyclic dependencies. So you as a developer don't have to worry about that. You can take a jar file, not have a module-info.class file inside the jar file, put it on the module path, and it automatically becomes a module. All the problems associated with exporting everything and having dependencies on everything will be solved by the module system itself. So now we do actually move away from Classpath hell, because now we don't have to have all of the explicit dependencies specified there. We simply say, here is the module path, where you can find the modules, and the actual dependencies, because they're encoded into the modules, or they're explicit from the point of view of automatic modules, will be resolved either at compile time or at runtime. So it eliminates the problems of having to do all these explicit jars. So just to summarize then, modularization is a big change for Java. It's, as I said, very much at the JVM and the JRE, the compiler level, rather than being changed to the language itself, rather than being changes to the APIs and the libraries, well, from adding new libraries. There are some potentially disruptive changes that are coming, various things that I've explained in terms of the backwards compatible, or incompatible changes that are in JDK 9. The encapsulation of private APIs, or non-public APIs, I should say, could cause problems. But if you've used only public APIs, won't be a problem for you. Developing modular code, you do need to sort of understand the details about that. There's actually a number of other things that I haven't had time to go through. So there's things like the way the class loaders work, because that has changed between JDK 8 and JDK 9. And so there's things like that that you need to be aware of. But once you get the idea, it will enable you to have a much more flexible system and ultimately a better way of developing and deploying applications. Just one thing I'm going to say as a kind of little bit of a, not exactly a sales pitch, but just to highlight here. As part of Azul, we have a thing called Zulu, which is our build of OpenJDK. So we take OpenJDK, we build it into a runtime, and we make that freely available. So if you're looking for JDK 8, JDK 7, or JDK 6, then you can get free versions of that from us. We also have early access builds that we do of JDK 9 as well, so you can do that. Now, there's no difference between our builds and other commercial builds of OpenJDK, except that we provide commercial support around it, and if you want to, you can talk to us about that. But we also have embedded versions of that which don't have a licensing fee involved, as other people do. Further information, OpenJDK.java.net is the kind of big place to go for the OpenJDK project, which is where all of the development of JDK happens. There are a variety of JDK enhancement proposals which are detailing various things in terms of changes. I mentioned a couple of those as we went along. And then there's also Project Jigsaw, has its own page. And there is this document called the State of the Module System, which does provide a lot more detail about the way some of these things work. And as I said, you can look at the details around service loaders and areas like that. And jcp.org, which is where the Java SE specification is being defined. So there's a JSR for Java SE 9, and so that will come out shortly, hopefully. Yes. So with that, thank you very much.